So very good morning to everyone. So we are going to discuss or say about the unit 3 of design analysis of algorithm. The title is dynamic programming and greedy technique. Here, what is first of all we have to discuss about what is dynamic programming. So dynamic programming is nothing but we have to divide a problem into n number of subproblems, and we have to overlap with the subproblems and storing the results to avoid the return calculation. So this is similar to the divide and conquer, but the one difference is we are going to overlapping the subproblems and storing the results to avoid the redundancy. And the greedy technique. So the greedy technique is nothing but we have to find a optimal solution for the subproblems or a problems. So we have to use n number of different data items to produce the optimal solution here. So the first topic of the third unit is knapsack problem. So what is knapsack problem? It is nothing but a combinational optimization problem. It is commonly known as the rucksack problem. Here we are going to, it is otherwise known as a container loading problem. Here we have to fill a bag of weight of a maximum weight of W, and we have to put n number of items. Each items has a separate weight and profit associated with it. We have to fill the bag with the maximum items which will produce a maximum profit, and we have to obtain that and I have to reach the total weight, which is a maximized capacity of the bag. So this is what the ultimate aim for finding the knapsack problem. Here we are going to see about or discuss about four different types of knapsack problem. The first one is fractional knapsack problem, 0/1, bounded knapsack problem, and unbounded knapsack problem. Here we are going to discuss about a fractional knapsack problem. Here the fractional knapsack problem is nothing but we have to divide the items based on the capacity and the weight which is obtained in the bag capacity. So first we have to given n items. Each item is associated with that values as well as the profit. The maximum capacity of the knapsack is represented as W, and the fractional knapsack is nothing but we have to break the items for maximizing the total value of the knapsack. This is what the difference between the 0/n knapsack problem and the fractional knapsack problem. So 0/n knapsack problem we have to solve by using the dynamic approach. Here it is just nothing but we have to divide the problems into a number of problems and overlapping that problem to obtain a solution. The fractional knapsack problem is solved by using a greedy approach. That is, we have to give n items or n input items to obtain the optimal solution. So in 0/1 knapsack problem, it is not possible to break the items, but here we have break the items for obtaining the maximization capacity in the bag. So 0/1 knapsack problems find a most valuable subset item with the total value less than equal to weight. Here the total value is equal to weight if the total weight of the items is more than or equal to the knapsack capacity. So here in 0/1 knapsack problem we have to take the objects in an integer value. In the fractional knapsack problem we can take the objects in a fraction as well as in a floating points. Here is a optimal binary search tree. So optimal binary search tree, which is nothing but we have to build a binary search tree with the optimal solution. Hope you know about the binary search tree. It has at most 2 children, and the left children should be lesser than the root value and the right should be greater than that root value. So here the sorted array of n keys of size n that contains a key to make the binary search tree, and an array of frequency n where the frequency of I is how many times the keys I is searched. The task is to find the minimum cost of the binary search tree to build that can be constructed using the given key. The cost is defined as the sum of frequency of all the keys multiplied by the depth. Here we are going to keep with the depth first search property. So this is what formula for the optimal binary search tree. We have to find the cost or node is equal to cost of the node is equal to frequency of the node into level. Here we are going to implement the optimal binary search tree in the depth first search manner, and the total search cost is summation of I equal to n into I to 1 into n into frequency of I into level of I, where level of I is the depth of the node with the keys I, the frequency is the frequency of that key. It returns the minimum value possible for the total search cost. The main application of the binary search tree is we have to go with the Google Maps like that. We have to find the optimal way to find out the particular location here. So this is what the recursive algorithm to find the optimal binary search tree. In this algorithm, we have to use a recursion to explore all the possible binary search trees that we have to formed with the given keys and their frequencies. Here we have these are the steps to find out the binary key value, and we have to construct the n number of possible keys. First, we have to choose a key between I and j as the root, and recursively find the optimal cost of the left subtree I to r minus 1 and find the right subtree r plus 1 to j. Add all the frequencies of the for all the keys. So the key frequency is nothing but the likelihood or regularity of looking for a crucial values. The objective is to find the lowest possible inputs. So the next topic is Warshall and Floyd algorithms. So before that, some of the benefits we have to go with the optimal binary search tree is it reduces the average time spent for searching the result, as well as to adjust to shifting the access patterns. So the next one is the Warshall and the Floyd algorithms. So both of the algorithm is used to locate the shortest course between all pairs of vertices in a weighted graph. Here it works only in the weighted graph. It works by keeping a matrix of distance between each pair and update this matrix iteratively till the shortest path is discovered. It is a dynamic programming algorithm used to discover the shortest path in the weighted graph, which includes the negative cycles also. It works with the aid of computing the shortest path between every pair of vertices within the graph. So the Warshall and Floyd algorithm works by maintaining a two-dimensional array that represents the distance between the nodes. Initially, this array is filled only using the direct edges between the nodes. Then it keeps on updating the distance by checking if any other shortest paths exist through the intermediate nodes. If any other shortest path is available, it will update the old nodes with the new one. This algorithm works both for direct and undirected graphs and can handle both the positive and negative weight edges. But the important note is it is not works with the negative edged graphs. So this is what the idea behind the Floyd-Warshall algorithm. Suppose we have the graph of distance of a two-dimensional array. We have to mention the distance in the two-dimensional array with the vertex 0 to v minus 1. So now we have to evaluate the distance, where the distance I and j, it represents the two nodes, where represent the shortest path between the vertex I to j. Now the vertex I to j has the intermediate nodes. The idea is to treat each and every node from the vertex k to 0 from 0 to v minus 1 as an intermediate node one by one. Why? Because we have to find the shortest path between each pair of the vertexes. This is what the ultimate aim for using the Warshall-Floyd or Warshall algorithm. So we have to consider the vertex k. We must have considered the vertex 0 to k minus 1 already. So we use the shortest path built by the previous vertices to build the shortest path with the vertex k. This is what the optimal substructural property in a Floyd and Warshall algorithm. So the time complexity of finding the Warshall and shortest distance using the Warshall and floor algorithm is O of V3. Here the V is the number of vertices in the graph. So we run 3 nested loops of size V. So the auxiliary space is 0 of 1, O of 1. This is what the real world application of Warshall and floor algorithm in the computer networking. It is used to find the shortest path between all pairs of the nodes in a network. So this is termed as the network routing algorithm. So in the aviation industry also, we have to find the shortest path between airports, and the geographic information system. It often involves analyzing the spatial data to find the shortest path. Clean's algorithm, which is a generalization of Floyd-Warshall algorithm to find the regular expression of a regular language. Thank you.